Okay. Welcome back, everyone. Let's get started. Please join me in welcoming Peter Armitage from the Johns Hopkins University, who will be discussing electrodynamics of quantum materials.
Okay, whatever. Yeah, thanks very much for the invite to come. I always really enjoy these schools. It kind of, I think we even professional talks sometimes, which of course we have a lot of seminars, but sometimes they proceed at a rate which is kind of too intense for even experts in the topic. And so when we have schools, it's very often, even for experts in the audience, kind of the right level. So I always enjoy sitting in the audience for them. So I was charged originally with giving some experimental overview towards quantum materials. That's, of course, an impossibly large topic. And so I'm kind of focusing at something a little bit closer to my expertise, and that is on optics of quantum materials. And so in the course of two lectures, I want to do two things. I mean, I yesterday spoke or led a discussion about, let's call it the future of quantum materials and experimental approaches to them. Talked a little bit about, some kind of far-reaching ideas about what to do with optics, rather speculative ideas. Now I want to talk a little bit in these two lectures about things which are a little bit more grounded, things of each other already happened or in the present happening. I've split up the topic into two subtopics, and I'll talk today mostly about linear response experiments, and those are interesting. I think they're important to talk about for two reasons. One, because linear response is, we're going to talk a lot about response functions in general, and linear response is, of course, the simplest version of a response function. So we're going to build up a lot of intuition in the context of understanding what happens in linear response. And then, of course, linear response is just important by itself. It's, as we'll discuss, most of what we know about material systems comes from driving them on their natural frequency scales. And linear response is simplest and powerful. And because of its simplicity, we can say a lot of things in a kind of reasonably model-independent way about possibly complicated systems. So that's what I'm going to talk about. Before I kind of get into, I'll also say that a lot of it is, particularly today's lecture, is particularly pedagogical. And so, as always, if there are questions, please interrupt me. I think that some of it will not be new to many people in the room, but I don't think all of it will be a review to anyone. And I hope even for experts, it's going to be interesting to how things will be presented in a somewhat novel fashion, and so that should be interesting. So before I kind of get into it and say some more preliminaries, let me just kind of give you a feeling for where we're going with this. We're going to be talking again about the electrodynamic response of materials, and one of the things we might like to understand, for instance, is the resistivity of the cuprates. So this is resistivity as a function of temperature, quite old data, for certain, probably that stopped working. Well before many of the students in the room were born, this data came along. There we go. And what we're interested in here, resistivity as a function of temperature, this is in lanthanum strontium copper oxide. That's the superconducting transition way down there, 30 or 40 Kelvin. And the remarkable thing about this data is that it's linear in temperature all the way up to the melting temperature of lanthanum strontium copper oxide, well over 1,000 degrees Kelvin. One of the other remarkable things about it is that it's linear and it just kind of smoothly passes through various different scales in the problem without any regard to them. Right? So one important scale is the lattice scale. And so the mean free, this is where we would estimate that the mean free path of lanthanum strontium copper oxide becomes of order the length scale, the lattice constant itself. But the resistivity keeps getting worse, and of course it's nonsensical to think about scattering of particles on length scales shorter than the lattice constant itself. There's nothing in there. And so this is something that people have been trying to understand for a long time. This is also dead. Can I get a pointer which works? Works. So, well, okay, it's working a little bit. That doesn't work at all. All right, I'll just have to point, I guess. Doug Nielsen to the rescue. Yes, thank you so much. Yeah. Ah, that's great. Yeah, thank you. So this has been called Planckian dissipation because if we infer scattering rate from this temperature dependence, a scattering rate of the rate that momentum or current dissipates in the electronic system, it goes like kT with a coefficient close to 1, right? So divided by Planck's constant. Now, some assumptions go into that, but if we measure the optical conductivity directly, this is the optical conductivity of a lanthanum strontium copper oxide film for a slightly overdoped one. The conductivity as a function of frequency shows this kind of notable peak, which is peaking towards zero frequency. And when we do these experiments, and I'll talk about it, we measure, this is the real part of the conductivity. We measure the real and the imaginary parts at the same time. But this function here has a width, and there's no assumptions that go into that. That width is just by definition the rate that current dissipates in a system. So you don't have to assume anything about masses. You don't have to assume anything about charge densities, temperature dependencies, anything. You can just read off the rate as a function of temperature, and the width is a function of temperature, giving you a rate as a function of temperature, and that just turns into this rate as a function of temperature you can plot, and it's linear in t with a coefficient close to 1 over some large range. So that's something we might want to understand. Yeah. Yeah, so you have to fit it to some functional form. And so when we're fitting this, we're assuming it's a Lorentzian. That's right, which is a good approximation at low frequencies. Yeah. And when we're fitting it not just the real part at this point, because you can see, as with any experiment, you're kind of spectrally limited by the technique. But we also fit to the imaginary part at the same time to help us constrain that. So it's this fitting of the real and imaginary parts of this response at the same time, which allows us to do this with kind of high fidelity. But it comes with an assumption. That's right. Yeah. So we'll talk more about that. Another kind of experiment that we might be interested in is this one here. Again, lanthanum strontium copper oxide, keeping it on the same page. This is the real and the imaginary parts of the conductivity, but where we've done experiments in very large magnetic fields. And so these are new data that came some years ago in collaboration with my group and a group of Scott Croker at Los Alamos National Lab and the National High Magnetic Field Lab, where we do experiments in large magnetic field. And here you can see this is conductivity, real part, conductivity, the imaginary part. We'll talk more about what this means in a moment, in a little bit, but plotted as a function of positive and negative frequency. And so what positive and negative frequency means here is the response to right-hand polarized light, let's say, where the time dependence is e to the I omega t, and the response to left-hand polarized light, where it's e to the minus I omega t. And it turns out when you're putting a material in magnetic field like this, that's a convenient way of expressing the data. We actually do the measurement in the XY basis, and then we can convert it easily to right and left. And then what you see from this is this peak here at zero field is peaked at zero frequency, and you put a large field on it, and the peak shifts. And again, we fit the real and imaginary part, and there's an assumption to this particular functional form. Here, there's an assumption that it looks like a Lorentzian, real and imaginary parts at the same time, and we can pull out this shift, and that shift is the cyclotron resonance. The shift is the cyclotron resonance frequency, EB over M, and so that's something we can also get from that data. Right. Okay. So I'll give you a bunch of examples all on kind of like metallic response, and then we'll talk in the rest of the lecture about what these things mean in more detail. But just again to give you a feeling for what this looks like, there is some conductivity data that is again real and imaginary parts. Apologies. Real and imaginary parts of the optical conductivity for a material, and I'm sorry I didn't write it here. Uranium, it's a heavy fermion compound, uranium, palladium, 2, aluminum 2, and sigma 1 and sigma 2, and these these lines fitting through it. That's again this Lorentzian Drude functional form. And the point I just want to make, you might take a look at the very different frequency scales here, terahertz of this width here, and gigahertz. This gigahertz of this width here. And that is already highlighting an important point, is that the frequency scales of solids span a very, very large frequency range, and will be something that we're going to have to take into account when we're doing our experiments, right? We're not going to have one single magic spectrometer that will be able to kind of span the whole frequency range of different important energy and frequency scales we'll want to look at. and also tells us that there are going to be different frequency scales that are going to be telling us different things. We may see, in both cases, we saw Drude response, but we saw very different functional forms. The lecture today is based primarily on this series of lecture notes that I wrote this first in 2008 at the 2008 Boulder Summer School, and it was not my intention for it to kind of become a living document, but I put it on the archive, and many people over the years have said what they thought it was a very nice and useful resource for them. This is all the way from beginning graduate students to senior faculty, and since that time, I've updated it on a number of different occasions, as well as just last summer with another visit of mine to the Boulder Summer School. So I'm going to hit, I can't, this is a really big topic, and I can't hit everything, but I'm going to hit some of them. This is what I wrote in 2008. The short review and lecture notes attempt to lay out the brief summary of the formalism, techniques, analysis used for optical spectroscopies for correlated electron systems. They are idiosyncratic, occasionally opinionated, and considering the breadth of the subject, incredibly brief. So, I like what I wrote in 2008, and we're going to kind of stick to this general strategy. Even for this incredibly brief set of lecture notes, we can't cover everything, obviously, today, and I'm just going to hit a few different highlights. So I'll tell you about response functions in general, and this will be both an introduction to response functions. It'll be useful for the particular thing about linear response that I'm emphasizing, but it will also set us up for tomorrow's lecture when I talk about nonlinear responses, which is a current topic of a lot of interest to people, as well as kind of a topic that my group is spending a lot of time on. We're going to talk about optical constants of solids, and that's, of course, the main thing that we're after. I'll talk about getting some intuition from simple response functions. I'll give some examples about simple metals. I'll talk about some more advanced things here, particular sum rules and some new developments that have happened in this regard, and then talk about techniques and use that as a way of introducing some particular examples of interesting physics that we can get out, which are going to talk a lot about metals and correlated metals, but of course, superconductors and magnets and topological materials of various kinds. Okay, good. Okay, so let's go there. So I think it's fair to say that much of what we know about physical systems comes from their response to finite frequency perturbations. Finite physical and chemical systems are typically characterized by a few frequencies. And if we drive the system at those frequencies, we can find resonances, right? And so that's true from everything from atoms to masses on springs to violin strings to whatever this thing is here. All of these systems have particular frequency scales, and we can drive them at those frequencies, and learn something about the systems from their response to those drives at the natural frequency scales. One great challenge is that if we're interested in condensed matter physics, the energy scales that we have to confront span an incredibly large range, right? So here's the electromagnetic spectrum, and we have, of course, different units that we'll use to specify these. We have different length scales that correspond to the wavelengths of light, different frequencies associated with the oscillation of the electromagnetic field, and different energies that are associated with the photons that come in. So if I'm thinking about, trying to characterize something about, let's say, structure and chemical bonding in materials, then I'm typically up in this range up here in the X-ray range, either hard X-rays or soft X-rays. Those are useful for characterizing the electronic structure associated with bonding, typically something on the order of 10 to maybe 1, something between 1 to 10 kile-electron volts ends up being an important and notable energy range to probe materials. The range which is kind of relevant for things like kinetic energy and kind of the bare interaction energies in solids are closer to the visible range. So we're talking about electron volt scales. If we start to think about the kind of effective interactions that come out between degrees of freedom that we might be interested in when we're thinking about cooperative phenomena of solids, an obvious one is perhaps the exchange energy in materials, right? One Heisenberg-like spin, and how does it talk to another Heisenberg-like spin, and a kind of a characteristic energy scale for that is about a half an electron volt, or maybe even a little bit less, a quarter of an electron volt, if I'm thinking about the exchange energies in systems, again, like cuprate superconductors. If I have magnetic systems that are built of maybe more localized orbitals, let's say 4F systems. This is relevant in the heavy fermion systems and some interesting pyrochlor magnets. The exchange energies are going to be much smaller, milli-eV scales. Tens of milli-EVs ends up being an important energy scale in many systems for the phonons. Those optical phonons, of course, the phonon scales persist down to much lower and, in fact, zero frequency if we're thinking about acoustic phonon scales. We can be thinking about maybe emergent scales that come out of systems like the scale of superconducting gaps. And I'm thinking about the superconducting gap scale, the binding energy between two electrons in a Cooper pair. In a high temperature superconductor, that's tens of milli-EV. But if I'm thinking about the energy scale that's associated with the binding energy of the Cooper pairs in a conventional superconductor, that's going to be much smaller, milli-EV or less. The energy scales in really low TC superconductors like heavy fermion systems can be in the tens or the micro EV scale. And so we're thinking here, we started up here in the kilielectron volt range, and now we're talking about the micro electron volt range. And so that's something like 10 orders of magnitude. And so that's our problem if we're interested in the electrodynamic response of materials, is to characterize materials over 10 orders of magnitude. So there's no, as I mentioned, no magic spectrometer which allows you to do that. And so that's something I'll talk a little bit about today. It's just the kind of spectrum of different techniques that we can use to understand it. Okay, very good. So, maybe I'll say one more thing on this is that one of the kind of challenges, if you will, if you're coming to this field from the outside, is the different units that are involved, right? So each kind of spectroscopy has their own particular kind of units that they're fond of. The thing that you can kind of remember, particularly for today's lecture, is something like 200 gigahertz, approximately equal to 10 Kelvin, is approximately a milli-eV, is approximately about 10 wave numbers. 10 wave numbers are kind of old school, almost Victorian era units that spectroscopists like to use. It's just inverse wavelength in units of centimeters. Okay? And to give you kind of a rough feeling for where thermal scales are, I've written down here 1K, 100K, 10,000K. And of course, that kind of spans the temperature ranges that we might be possible. The low end spans the temperature ranges of things that we might be interested in manipulating and kind of putting the temperature in a particular environment like that. But and they correspond to different frequency scales in this fashion. One kind of important point that comes out in the study of cooperative phenomena of solids, if I have some material which has some interesting physics which happens, let's say, at some particular temperature, very often frequencies in the order of that temperature in an important scale, right? So that maybe the canonical example of this would be superconductivity. If I have a superconductor which exhibits some superconducting transition at, say, 10 degrees Kelvin, frequencies on the scale of 10 Kelvin, where I go from Kelvin to energy with Boltzmann's constant and then to frequency with Planck's constant, those frequencies end up being an important energy scale because that's the binding energy of the Cooper pairs. Okay. So where do we get started with this? Typically, we're going to get started thinking about a perturbative understanding of the effect of the electric field on a material. And so if I'm thinking about electric degrees of freedom, this will be thinking about that there's a polarization induced in the sample by an applied electric field. The lowest order term, that's the linear response, and that's what I'm going to be talking about today mostly. But there are these higher order terms. Some of them are allowed by symmetry and others are not allowed by symmetry. This term here, for instance, is only allowed if I have a system which breaks inversion symmetry. There's typically strong symmetry constraints on the even terms and less severe constraints on the other one. This is the polarization, that's, say, the conductivity, and unsurprisingly, there's a relation between the polarization and the conductivity, and hence a relation between the electric susceptibility and the electrical conductivity. These nonlinear responses is something I'll talk about tomorrow. The linear response is the simplest, and it's very powerful. We're going to see when we talk about nonlinear responses that it gets a lot more complicated really fast. And so if we're going to think about complicated materials with more complicated probes, we better have a very good reason for doing that. And so that's what I'll motivate tomorrow. Now we're going to be thinking about linear response because it's the simplest and it's powerful, but of course, it's not the only thing. See if I can get this thing a little bit better here. It's kind of, there we go. That's going to work better. Okay. Okay, so where are we on this? One of the things, because we like linear response, it's the simplest and it's powerful, we can say a lot of interesting things about the linear response, kind of without resorting to specifics about about particular materials from quite general considerations, right? So things like symmetry and general considerations where on response functions like causality are very useful in guiding us. So there is such a thing as Neumann's principle, and this so-called Neumann's principle states that the symmetry transformation of any intrinsic physical property of a crystal, such as a response function, must include at least the symmetry transformations of the point group of the crystal. Right? So what this means is that, let's say I have a conductivity, and the conductivity is a tensor. The symmetry properties of the tensor have to include at least the symmetry transformations of the material. I may have a simple tensor like linear optical conductivity, or I have a more complicated tensor like some nonlinear response. But in either case, these kinds of things are the same. When we're even thinking about the simplest case, this is a very important, there are very important possibilities here, which guide us towards being able to kind of get some, in some cases, even quantitative understanding of our data without a particular microscopic model to guide us. And so that's quite important and useful. The thing that I want to emphasize here, and the thing that's emphasized in my lecture notes, is the importance, perhaps at first pass, of thinking about the optical response in terms of scattering matrices. So in the previous slide, and after this, I will be thinking and telling you about what insight we can think about response functions. If I have a polarization, I push on the system with electric field, there's a susceptibility which connects these two. Right? But often, we don't measure a polarization directly. Right? What do we measure directly? We send an electric field, we scatter light off of the sample, and then we measure an electric field in the far field. And so it's quite useful for us to think about the scattering matrix, which relates the incoming field to the outgoing field, and the symmetry properties of the material that are related in that fashion. And so in the simplest case, and optics is a kind of very simple example of how you can conceive scattering matrices in this regard, we're going to think about a 2x2 matrix, which relates incoming fields. And so here I'm going to imagine, for instance, I have an electric field propagating in the z direction, and I have the electric field has polarization components possible in the x and y directions. I have a sample, which is its scattering is represented by this T matrix, which goes by the fancy term Jones matrice, but it's really just a 2x2 matrix, which relates the incoming electric fields to the outgoing electric fields. Okay? We can maybe make my notation a little bit simpler here. Instead of talking about TXX and TXY, TYX and TYY, I'll refer to them as A, B, C, and D. And again, coming back to the Neumann's principle, the symmetry properties of this 2x2 matrix reflect the symmetry properties of the material itself. And so I can do something very simple. For instance, perhaps I know I have some material that has a C4 symmetry. I take the material and I turn it by 90 degrees and I got the same thing. And so that should reflect itself in the scattering matrix. And that's an exercise that I can go through. If I have a rotation matrix, 2x2, I let phi here equals to 90 degrees. I can take the T matrix here and rotate it and have the T matrix have to equal the T matrix before rotation and after transmission have to be equal. And when you okay, that's the rotation matrix and we can rotate it. It's all done right here. So this guy here has to equal that guy there. And in so doing, there's a relation between A and D and B and C. And so if I have a C4 symmetry, my matrix has that particular form. Okay, so it is kind of equal diagonal components and opposite off-diagonal components, right? So a very simple case. But I can keep playing this. That's a kind of very simple case, but I can keep playing this game that's for rotation matrices with 90 degrees, or matrices which, should have a symmetry of 90 degrees, but I could have a C3 symmetry, I could have a C6 symmetry, I could have reflection symmetries, I could have various combinations of reflection and rotation symmetries. I can think about the consequences for time reversal symmetry on these matrices. I can think about the consequence of having a material which perhaps where neither time reversal and inversion are symmetries, but the product of the two. And from these kinds of considerations, you can put constraints on them. This generally shows up as some kind of algebra between tensor components. Here it's done for the super simple case of a 2x2 matrix and these scattering matrices in linear response, but the notion is still valid for the situations we'll talk about tomorrow, where we can think about nonlinear response and they're kind of higher dimensional tensors which have different considerations that go into it. Okay? The case of time reversal symmetry, in fact, is really important. The time reversal symmetry, having it or not having it, is important as an important consideration in many ordered states of matter. And even one might think that this is all kind of quite established stuff, but it was actually even just up till a few years ago where these aspects were being kind of intensely debated about whether or not it was required to have a breaking of time reversal symmetry, as you do, for instance, have, let's say, in a ferromagnet, to be able to get a Kerr rotation of light. So Kerr rotation is light, let's say, linearly polarized light incident on a sample, being reflected off the sample, but when it's reflected, it's rotated. And so the question is, you certainly get that in a ferromagnet, but there are other states of matter which break time reversal symmetry, perhaps in less obvious ways. There are also states of matter, let's say, systems which are chiral, which are known to have rotation of the light in transmission, but it was debated whether they could have light in reflection or not. So rotation of light in transmission sometimes it's called Faraday rotation. It can be also called circular optical activity. And these kinds of considerations were important for solving those debates. Okay, good. Very good. So there's that. That's one thing. So symmetries. Important takeaway message is symmetries are an important constraint of materials that we can use even when we don't have some microscopic knowledge of what's the microscopic equations or microscopic understanding of the system. Of course, generally our starting point for further understanding of materials is Maxwell's equations, which I won't go over, and some general constitutive equations which relate things like displacement fields and electric fields and polarizations to each other, either for the electric degrees of freedom or for the magnetic degrees of freedom. Right? So we usually parameterize this in terms of some proportionalities, which are these response functions I talked about. That's the conductivity of the current is proportional to the electric field. These are all valid, of course, in linear response, displacement fields, polarizations, and a lot of what I'm going to say, I'm talking mostly about electric degrees of freedom, also apply to magnetic degrees of freedom, and you have things like the magnetic susceptibility in this fashion. Right? We can think about the for electric degrees of freedom, we can think about the electrical conductivity, we can think about the dielectric function. These are related to each other by, depending upon what particular unit system you like, by this relation or other relations, depending on if you're in SI or in CGS units. But the real part of the conductivity is related to the imaginary part of the dielectric function by this particular relation. And it'll be important for some of the considerations I'll talk about in a little bit that we need to identify that the conductivity is proportional to the real part of the conductivity is proportional to the imaginary part of the electric susceptibility. Right? So we're going to I'll point it out when we're going to do this, but we're just going to imagine we can kind of go back and forth with relations like this. Okay, good. So it's very often the case when we're going to start thinking about again, we're going to start from general considerations. And when we're going to start from general considerations, we're going to kind of start from the most basic things we can. And we're very often going to start to think about the response of a system in terms of what we refer to as memory functions, right? So we can think written here for the displacement field, or perhaps more usefully here in terms of the current. But where we're going to think about a current in space and time being caused by an applied electric field in space and time, and with a conductivity which is defined over various indices in space and time. Okay? This is called a memory function, perhaps for obvious reasons, right? It encodes the current is not just a instantaneous function of the present electric field, but is of course a function of previous electric fields. If I push on something, whether I push on a shopping cart or if I push on charge with either my hands or electric field, I can push and then it starts moving. So it can have a velocity after I've pushed on it. That's just an obvious statement. But velocity is current with appropriate unit transformation. And so the velocity of an object now depends upon the forces in the past. And so ergo memory function. And this is just how you write one down mathematically, right? So you have a conductivity in the time domain, electric field in the time domain, and then a current in the time domain in this fashion. And I won't go through the details of all of this, but this is all this kind of basic things, and also discussed in my notes. Very often we're going to find that it's more useful to kind of portray our data as well as conceive of the problem, not what happens in the time domain, but what happens in the frequency domain. And we can just get there by simple Fourier transform, where we're going to think about those quantities which we might originally have considered in the time domain and these memory functions, where we had the memory function was essentially a convolution. If I have convolution in the time domain, it turns to multiplication in the Fourier domain, which is one of the reasons why it's so useful. So we're going to think about defining quantities in the frequency domain as such, right? So we have the current defined as a function of frequency to a time-dependent field of which will have different amplitudes at different frequencies, and then a conductivity, which is our response function, which we'll define in this fashion. Now, the conductivity in the time domain is a real quantity, corresponds to a real current. But after we kind of go through this business and we go and we Fourier transform and write it down in this fashion, it's a complex quantity. And I'll keep making reference to this because it's important, but there's an example of the complex conductivity, this of a not particularly complicated material, but n-doped gallium nitride. So just a kind of canonical semiconductor. This is the conductivity as a function of frequency. This is the real part, and that's the imaginary part. And this lines that go through it are just fits to the Drude expression, which we'll talk about in a little bit here, right? So the important thing I want you to take away from that is that the conductivity is a complex quantity. It is the real and imaginary parts. And it's not that the real part, sometimes, real part gets more attention, but they really just reflect the same underlying responses, right? So they come from this memory function in the same way. And in fact, for some materials, it's actually the imaginary part, which kind of tells us more immediate information. If I have a superconductor at low frequencies, it's the imaginary part of the conductivity, in fact, that I'm more interested in, which encodes more of the information I might be interested in using. Okay, so that's one thing. Complex quantities are essential. One thing that's an advantage of optical responses, we'll find that there's a correspondence between what can be measured in experiments like terahertz spectroscopy when you look at magnetic systems, where we can measure the magnetic susceptibility, and that has a very close correspondence to things which are measured in neutron scattering. When we're doing experiments with the optical conductivity, unfortunately, we only can measure at zero momentum. But the advantage of doing that, let's say over neutron scattering, is you get the real and the imaginary parts at the same time. And that can be very useful for analysis. Okay. So complex responses are something that we're going to make lots of use of. Now, the other thing that I'm going to mention, and I'm not going to really go through here in detail, but the considerations of what is typically referred to as causality are important. And again, fall in the class of things that allow us to kind of make strong statements despite not having microscopic models. And the notion of causality just means that responses have to come before their causes, right? So if I push on something, it moves after I pushed on it and not before. That sounds like an obvious thing, and it is, but it has really important consequences in the structure of the response functions. Okay, so I won't go through and do these derivations for you in detail. I'm just going to cut to the chase. But these are codified in what we refer to as Kramers-Kronig relations, right? So they basically have their origins in the causal structure of the Kramers-Kronig relations are going to relate the real and imaginary parts of quantities to each other, real and imaginary parts of the frequency-dependent response functions, and they have their origins in the causal structure of those quantities in the time domain. Okay. So that's kind of a very basic thing that just comes out of it. And there's a particularly kind of simple derivation of this as applied to the conductivity in my lecture notes. I won't go through the details of it, but this is the important part right here. So if I have a real and imaginary conductivity, and let's say I know the imaginary conductivity for all frequencies, 0 to infinity. I never will, of course, but I might be able to approximate it. Then I can figure the real part at any frequency. Okay, that's important. If I know the real part at all frequencies, 0 to infinity, I can get the imaginary part at any frequency. Okay? The Kramers-Kronig relations are tremendously powerful for us. Not typically in the form that we would have them here, but more often we might know the real and imaginary parts of a quantity over a limited frequency range. I'll show you data like that. So we know sigma 1 and sigma 2 over a particular frequency range. We know both of them. And we can use our knowledge of the Kramers-Kronig relations to tell us things about parts of the spectrum that we haven't actually measured. So that sounds perhaps a little bit like magic, but in fact, this is what we do all of the time when we're measuring a quantity like the superfluid density. So superfluid density is denoted as in a superconductor or a superfluid, let's talk about superconductors, the conductivity at zero frequency is a delta function. It's a delta function which has a particular area, and an important physical quantity is the area that is in the integrated weight in that delta function. Now, I can't measure the delta function because if I try to measure the conductivity at zero frequency, it's infinitely large. So I got to stay away from zero frequency. But by Kramers-Kronig, I know that if I have a delta function at zero frequency, my imaginary part will go like 1 over omega with a coefficient which is related to the strength of the delta function. And so this is what's measured all of the time. People will say they've measured the delta function, but in reality what they're measuring is the superfluid response, which is coming from this kind of inertial response at higher frequencies. Okay? And that's something we know we can do that because of Kramers-Kronig. Now, I'll show you a few other things that come out of this in a moment about the use of Kramers-Kronig, and that is a kind of a different consequence, and that's the idea of using them to construct sum rules, which, again, are important and terribly useful for us when we don't have microscopic models to guide us. Okay, good. Okay, yeah. Oh, maybe one other thing about this first. These are not all the Kramers-Kronig relations that exist, right? So there's a relation between conductivity and susceptibility, and so if this is true, there should be also ones for the susceptibility. But there are a lot of complex functions that can be used to parameterize the electrodynamic response. I could think, instead of thinking about conductivity, I could be thinking about the index of refraction of the absorption coefficient. And there's quantities which can be related in this way. I can very often I can think about the complex resistivity, in fact, and there's Kramers-Kronig relations that relate one of those to the other. And so that's something that we're going to use again in the analysis of our data. Okay. Simple models. Now we can start thinking about making assumptions about how do materials behave. And we maybe have a complicated many-body system that we don't really understand the details of it, and we're going to make some arbitrary assumptions to kind of try to start to hang our data on it to understand some things. If we're going to make arbitrary assumptions, they should certainly be simple. And so the simplest assumptions that I can make is just when I start thinking about the conductivity, I can start thinking about simple semi-classical models which is basically just Newton's second law for how does a time-dependent acceleration of charge from an electric field, how does the acceleration behave in response to an applied force which comes from the electric field, and then a particular damping, let's say, of the velocity which comes in with a characteristic time. So I can just kind of assume simple harmonic motion by performing some substituting in, getting this expression for the velocity. It looks like this particular form. Velocity is related to current in this particular way. And so that's the current as a function of some electric field at some frequency omega. And we've already used this relation here, J equals sigma E, which is just Ohm's law. And so we can write down an equation for the frequency-dependent Drude conductivity in that particular fashion. Now, you might say, like, who cares? Because this is some ridiculously simple model. But in fact, many interesting and important materials fit this simple exponential relaxation form in the time. Exponential relaxation in time gives us a Lorentzian in frequency, and it fits it very well. Right? So that's the data that I showed you earlier in uranium, palladium 2, aluminum 2 at this very, very low frequency scale. The lines threading through this data here, these microwave data, are a fit to that simple form, and the simple form fitting into it, we got a bunch of parameters in that, and we're going to, even at the quantum level, those simple parameters hold up. I mean, this is an interesting point, is that the simple classical result, actually a quantum mechanical treatment gives you to leading order the exact same thing, so very often we just will use the classical result to start to understand what's going on with the data. Yeah? Yeah, so about the oscillations here, right? So this is, again, the conductivity is a function of frequency. This is done in the microwave range, so that means gigahertz here. Different techniques measure these quantities in different ways. And so the way this is done is by taking a coaxial cable, a few millimeters wide, and taking a sample, which is a thin film of this material. Actually, silicon too, I thought it was aluminum too. I think I miswrote that. But anyway, it doesn't matter. This coaxial cable is terminated by a thin film of this. And microwaves propagate down this coaxial cable, hit the sample. And it turns out that if the sample has a resistance close to 50 ohms, all of that radiation is absorbed, excuse me. If it deviates from 50 ohms, it's what we call the impedance of the cable, some of the radiation will be reflected. And we can do that in a phase-resolved fashion. So we basically look to see how much radiation is reflected and what's the phase of the reflected radiation, and we can work that out to the conductivity. So that sounds all very simple, except microwaves are coming down from this generator. Maybe they hit a connector. Most of the microwaves pass through the connector and they hit the sample. But some of the microwaves hit this connector and the connection's not perfect and it's reflected back to the detector without ever hitting the sample. Some microwaves make it past that connector, hit the sample, reflect back to the detector, but they hit that connector from the backside and they're reflected back. So it's a big mess, right? The way to understand all of this was fortunately worked out by people who were first building telegraphs. So to put across transatlantic lines, right, from New York to London or from New York to San Francisco in the 1860s and 1870s, that was a similar problem. How are you going to send a signal on a noisy transmission line over great distances, right? That's probably even a worse problem than doing experiments on heavy fermions at low temperatures. These reflections can all be removed by a kind of a careful calibration scheme. But that calibration scheme is imperfect, and you still have kind of spatial resonances that come in from these multiple reflections in the line. And at some low frequency, it just doesn't work so well anymore. And so these are noise at some level, but what it is systematic error that's associated with the measurement technique. The important lesson that comes from this, again, is that for a microwave technique, this is actually tremendously good, right? You're talking about more than 2 orders of magnitude in frequency. And it still is something we would like to do a better job than that, but we're still kind of limited by the technique on either side, right? So we had to pick we were interested in this problem, we had to pick a particular technique, and it's still limited to a particular frequency range. And the technique just starts to fail outside of that range. And that huge oscillations there are kind of an example of that. The particular experimentalist decided to, plot into the range where things got messy, but Doug's one doesn't work either. But it's decided to move into this range where things got messy, but that's the takeaway from that. Okay, good.
Directly measured.
That's right. In this, they're reasonably directly measurable. There's no Kremers-Kronig performed here, if that's what you're asking about. Yeah, well, I think you can see that here in the sense that you fit with a Kremers-Kronig consistent form. The Drude response is Kremers-Kronig consistent. Yeah, so the smooth curves are Kremers-Kronig consistent, and so the data is Kremers-Kronig consistent to the extent that those curves are a good fit for the data. I would put it like that. Yeah, we don't often kind of go back the other way, but you certainly could. Yeah, people usually work hard to get the frequency domain data, and the other difficulty very often is that in terms of kind of reconstructing the frequency. Yeah, there's a bunch of technical details. It's not done often, but in principle, it's possible. Let me just say that. Yeah. Okay. But other questions? What time did I start, by the way? 20 minutes. Okay, fine. Okay, good. So let me use this idea now, some rules. So let me use this idea of Kremers-Kronig and complex response functions to kind of start to learn something that are interesting. So here is something that we use all of the time in optics, and that is the notion of sum rules. Okay? So if I have, let me pick one of these Kremers-Kronig relations, and it's the one that tells me if I take sigma 1 and I know it for all frequencies, I can get sigma 2. Okay? And let me imagine now I'm going to consider some frequency. I want to know sigma 2. It's some really high frequency. Okay? Much higher frequency than I have any structure in sigma 1, right? So there's going to be some kind of low frequency regime where I have some absorption. Sigma 1 is the dissipative part of the response. And here I want to think about some omega, which is way, way, way bigger than that range, where sigma 1 is 0. Okay? Well, so I can come up with some, if I start with that version for a Kramers-Kronig, I can get a form for the integral when omega is much, much bigger than omega prime. And then I get that guy there. And if I have, let me see if this one is working again here. No, but you can see that I have omega squared inside the integrand and the omega in front. Those omegas cancel. If I go to infinite high frequencies, can assume I know the functional form for how does the conductivity look, right? So if I go to mega electron volts, the electrons don't know they're bound. Think about that in the context of a hydrogen atom has 13.6 eV binding energy. But if I probe a hydrogen atom at a mega electron volt, it doesn't know that it's bound versus it's in the continuum. So that's a free electron. So I have the free electron form at high frequencies. And so I can just equate these. And what I find is that there is an integral, an expression. If I take the conductivity and integrate it all frequencies, I'm returned with some constants, things like pi, fundamental constant of nature, the electronic charge squared, and then the density of the electrons divided by their mass. Okay? So that is like, if you can't depend on these kinds of sum rules, you can depend on nothing else in physics. That's, as surefire as anything gets. Very often what we'll do, we never measured infinite frequency, of course, and very often what we'll do in the analysis in optical experiments is we'll take advantage of what we call partial sum rules. So instead of running out the integral to infinity, we run the integral to some value. Here I call it W, the bandwidth of something. And so if that W is like some really low energy manifold of states, which are maybe relevant for a system like a heavy fermion, where I have some really kind of low energy coherence scale and perhaps some very narrow band which forms in response to a Kondo interaction, and so that omega is a really small value, then I'm going to pick up a very small number on the right, which corresponds, if it's a small number on the right, that corresponds to a large mass, which is what I would get in a heavy fermion system. Right? So that's one thing I could do. I could also say, for instance, let's imagine I know the mass and I can use it to figure out some kind of I can imagine taking that W and having it as a running scale and trying to understand how is this sum rule kind of fulfilled at larger and larger energies as I kind of integrate out to higher and higher energies. And one of my favorite plots in condensed matter physics is just exactly that. So this is a plot of various quantities. So I mentioned that there are different Kramers-Kronig relations, and because there are different Kramers-Kronig relations, there are different sum rules that come out. And so we can have sum rules for the optical conductivity. That's it there on the upper left. So omega times the imaginary part of the dielectric function is sigma 1. But I have other quantities. I have the imaginary part of 1 over the loss function. It's 1 over epsilon. There's a sum rule that's associated with that. There's a sum rule that's associated with the absorptive part of the index of refraction. That's the one on the lower left there. And they're all kind of different in different ways, but you can see that in all cases, they basically equal the same thing on the right, which is a quantity we call the plasma frequency, which is equal to, okay, there's some pi's, the density of charges times the electronic charge squared divided by mass. Okay? What mass? Well, if I put in the free electron mass to that, let me put in the free electron mass and then kind of sequentially do this integral out to higher and higher frequencies. And that's what you see here. And so let's concentrate on the data for epsilon 2 here. This is the kind of, if you will, the effective number of electrons that I see by performing this integral out to some particular frequency. And so for really small frequencies, say 100 millielectron volts, right? You get a number which is really close. This is for aluminum. You get a number which is very close to the number of valence electrons for aluminum, right? So if I integrate out to 10 eV, aluminum is kind of a conventional material. It has big wide bands. If I integrate to about wide band, the bandwidth is about 10 electron volts. So I integrate to about 10 electron volts. I get all of those valence electrons. If you talk to a chemist and you ask them how many valence electrons does aluminum have, you don't have to. You can just read it off from this plot here. It's 3. But if you keep going, right now, it's not the valence electrons. It's kind of like deeper core levels, and they're exist at different energy scales. And as you keep integrating, you hit like 100 eV, and these go by various names that X-ray people have given them: the L edge, the K edge, and on and on and on and up. What's the atomic number of aluminum? Well, if you didn't know, you can read it from this plot. It's 13. right? So this, and where do you have to go? You have to go out to 10 to the fifth electron volts, right? So very high energies. So this is one way of thinking about data. And again, as I said, this is some old paper, but it's one of my favorite plots because it really kind of shows, again, one, these tremendously large energy scales that we have to think about accessing, important for solids. We may be concerning ourselves with kind of the low energy emergent degrees of freedom of a system, which are in the lower left of that plot. But of course, that's the nature of how interactions work. They are contingent upon what those low energy scales, what the effective parameters are contingent upon what happens at higher frequencies. Okay, good. Yep. This is data. Yeah.
Different leaks at different frequencies?
Yeah, different techniques at different frequencies. Exactly. That's right. Yeah. So, how, I don't remember it's all written in this paper. I don't remember the details of that, but exactly right. Different techniques at different frequencies. And I also suspect there's a little bit of artistic freedom with how do you connect the dots between points. But let's think about the religious lesson that comes out of this, and less about it was in 1978. I guess we could do a probably much better job now, particularly on the X-ray stuff. Okay, so that's one thing. That's where I have basically let this sum rule, the upper bound of it, run, and I'm assuming that the mass is a constant thing. Right? So I assume the free electron mass, and then I'm getting this kind of effective density as a function of frequency. But I can do something else as well, is I could just integrate, I could assume I know the number of electrons in the system, and I typically do know the number of electrons, and I can do this integral out. You saw when I was looking at that, showing you those Juder response, most of the optical conductivity was kind of in this low frequency peak, or there was kind of a well-defined peak at low frequencies, let me put it that way, and I could just integrate that. And if I do that, I get this plot, which is also one of my favorite plots to show. On the left-hand scale is the effective mass we get from integrating the low-frequency Drude response. And you see for lots of different materials, right? So down at the lower left, these are as uncorrelated materials as we have. Then we get a little bit more correlated iron, which is a ferromagnet, niobium, which is a kind of a conventional superconductor, manganese, which is not magnetic but is almost magnetic. Then things get a little bit more interesting until you get to the heavy fermions on the upper right. On the horizontal scale is the heat capacity, which in simple free fermion language is proportional to the mass. And so I find this really one of the most remarkable plots because it really is a demonstration of the quasi-particle concept. It's not obvious that when you get this soup of 10 to the 23rd, 10 to the 24 electrons, all with charge, all interacting with each other, you cram them into some tiny little volume, that the degrees of freedom that we could understand the material best, which now we would understand for Fermi liquid as quasi-particles, right? The degrees of freedom conspire to render us with excitations, which are very much like that of the normal electrons in the system. Because there's this proportionality between these two totally different ways of measuring mass. In one case, you're really measuring the inertial response. You're taking a material, time-dependent electric field, you're shaking it back and forth, and you're basically seeing what's the inertial mass from shaking these with a time-dependent electric field. In the other case, it's the heat capacity, and so you're seeing how much does the temperature change when you introduce a little bit of heat to the system, right? So in a free electron model, these are giving you the same mass, but there's a rough proportionality between them in these kind of more complicated systems, right? There's a lot of details when I present this. I present this plot sometimes in the context of some talks that I'm giving on experiments we're doing on cuprate superconductors, because I think it's a remarkable plot and a good plot for the reason I just said. It's really a demonstration of the quasi-particle concept. On the other hand, I think it's a bad plot because it overstates the case. And in fact, there are different ways we can think about defining mass, and these are not always the same, even for a Fermi liquid. But this is a different talk into itself. Okay, good. So that's some rules. Let me say that's some rules about the kind of conventional sum rule that comes from what we might call it really derives from the F sum rule. It's a sum over the absorptive response of a system. Here the conductivity, or if you put it differently, the first moment of the electric susceptibility, the dissipated part of the electric susceptibility. To make a connection to some things that were said by Joel Moore yesterday, he in fact mentioned another kind of set of sum rules, although it wasn't quite put in this language, and that is what is referred to now sometimes now as the SWM sum rule, coming from Sousa, Wilkins, and Martin. And I learned about this just a few years ago and really was quite, I mean, I was amazed that you know, the sum rules aren't very complicated. You take a response function and you integrate it. So how on earth could we have like a new sum rule? Like how is such a thing even possible for such a simple object? The Sousa, Wilkins, Martin sum rule, but in fact, there are people who have kind of, this is one of these things where it's probably best to not have been the first person to discover something, but to be the last person to discover it. So it's something which kind of keeps coming up on a number of occasions. But the basic idea is you take, let's say, the imaginary part of the susceptibility, or the real part of the conductivity divided by omega, right? So these are the same thing up to some constants. And in modern language, this was first pointed out by Kudinov in 1991 in a paper that basically wasn't read by anyone in the late, it was never translated from English. It's in a Russian journal. Kudinov himself translated it and put it on the archive in the late 90s after he noticed there was interest in the topic. But what he pointed out was that for an insulator, the integral of the imaginary part of the susceptibility, not the conductivity, but the imaginary part of the susceptibility is a bounded quantity. And you can show that it is related to the zero temperature, it's related to the length scale that's associated with the 0-point fluctuations of the polarization. So in a metal, this is a quantity which diverges, but in an insulator, it's finite. And he was able to show that through quite general considerations from the fluctuation dissipation theorem. It's, of course, it's a different sum rule that I was referring to before. But in this expression on the upper left, that delta D, that's the length scale of the polarization fluctuations in the system. So some time went on, and now there's been a number of different things which have happened recently. 2000, there's Sousa, Wilkins, Martin, who basically rediscovered this. That's an expression there, real part of the sigma divided by omega, which is equal to imaginary chi. And what they showed is that if you're dealing with, and they were thinking about this in the context of band insulators, that if you perform the sum rule, you measure the data and you perform this, that if you have a particular model of band insulators, the quantity which comes out on the left is the gauge invariant part of the Wannier functions, or was gauge invariant, excuse me, as they say, the Wannier spread. Essentially the smallest representation for the Wannier functions in a system, right? Which is kind of a remarkable thing. Wannier function it's the size of a microscopic wave function, but nevertheless, if you know the density of charges in the system, right, it's divided by 1 over n there, you can relate this to the size, this macroscopic wave function can be related to the size this macroscopic wave function, excuse me, this macroscopic response function can be related to the size of the wave function, which is a remarkable thing. Okay, there's been other more recent work on this, and this was actually implied, although the language wasn't used as much in this SWM paper, but there are other more recent papers by people like Raquel Quiroz or Liang Fu and collaborators, where they show that the same sum rule is related to the trace of parts of the quantum geometric tensor. So, or excuse me, the real part of that, the quantum metric. And so that's what's represented here on the left. So there's a number of different threads that are all coming together here. And the other thread that I would point out in this is that this quantity, the integration of the susceptibility, is actually the same thing that we heard about in Qimiao's talk yesterday, when it put in a different language altogether of the quantum Fisher information. So the quantum Fisher information is a measure of, it's a bound on the multipartite entanglement of a system. So I'm thinking about a spin system. Essentially, how many spins do I have to use to kind of build the smallest spin subunit, which I might then eventually use to build a larger extended state in the system. So that's written in the language of the number of spins. What I told you about Sousa, Wilkins, Martin was talking about the size of Wannier functions. So if I divide by the lattice constant, that tells you basically how many sites in the Sousa, Wilkins, Martin language, how many sites are involved as being the smallest size that I can basically localize a wave function. So this is where something, was known, something else was known, and a lot of stuff is coming together, but there's this deep relation between the polarization fluctuations and this concept of quantum Fisher information that comes from quantum metrology. So I was just going to show something about the quantum Fisher information. This is from some data from Alan Shea, but I think I'm just going to I've got a few more minutes left. Let me just kind of show a few more things about this. And this is from another paper of Sousa and Martin, along with another collaborator. And they basically just show that you can use the sum rule basically to bound the size of wave functions. This is for some materials that we might not be as interested in the quantum materials community, things like diamond or silicon or gallium arsenide, but nevertheless are important benchmarks. It gets more interesting when we start thinking about maybe topological systems where these sum rules are relevant for that kind of considerations as well. This is a paper from Raquel Quiroz in her group where she looks at it's put in again in slightly different units. And in fact, I think this kind of expresses how new all of this is that every person who kind of does something on this expresses it in a very different way. There's no standard notation. Even if the integral they're essentially writing is the same thing. And this is written in some notation which makes reference to being able to get at this quantity through the trace of the geometric tensor. But there are materials which are, say, have a very small values here, which are, say, atomic or ionic, covalent bonding, and then topological materials, say, like topological insulators. The length scale, there's no, as Erzberg mentioned, if I have a topological system, there's no way to exponentially localize the wave functions. And so the length scale that's associated with this integral is essentially the unit cell size. Right? So they're not exponentially localized. It's the unit cell size itself. And you can see this again, different language altogether. This is a paper by Vanderbilt, but where they looked at just a Chern insulator, and that's what's plotted here. It's basically at the top is the result of doing this integral of the optical conductivity as a function of some tuning parameter as you move from Chern insulator to conventional insulator. And you can see there's kind of like a logarithmic divergence as you move from Chern 1 to Chern 0, C equals 1 to C equals 0, a small peak. And this is just really a new way of understanding how to make use of optical response functions. I've showed you mostly theory here, and there hasn't been a whole lot except for looking at things like silicon or carbon or gallium arsenide, big band gap insulators. There hasn't been a whole lot of use of this in experiments, particularly on kind of more popular materials nowadays, but I think there will be. I hope we have a paper on this soon. Okay, am I basically out of time at this point? Okay, then I think I will just stop there for now. I'm happy to take any questions. Tomorrow I will continue and I'll talk a little bit about linear response techniques. We've kind of built up the language now, and so we can use that to learn some things about materials. So I'll tell you a little bit about the techniques and then also show the data that comes out from that and the kinds of things that you can learn. And then I'll talk about nonlinear response. So, okay, I'll stop there.
Are there any questions?
Right. And but the Armitage, right, from neutral scattering.
Yeah.
It's quite different, right? In the case of the Armitage case, purely spin response, right? I mean, it's a by the Q. Also.
Yeah.
In your case, it's zero, right? And also, you have evolve both the spin and charge.
Right.
How do you?
Well, yes and no. So when we're doing an experiment, we're indeed measuring response function at Q equals 0. The quantum Fisher information as inferred from neutron scattering is a Q-dependent quantity. And so we're in principle measuring the Q equal. What's that?
Well,
yeah, so we pick up Q equals 0, right? So in our experiment. So it's the important question is whether there's interesting momentum structure. And in some systems, there certainly are, right? So if I'm thinking about ordering of an antiferromagnet and pi is an interesting, important wave vector, then I certainly would miss a lot of information by doing an optical experiment on it. The general prescription to how to identify quantum Fisher information with the integral of susceptibility, that's a very general thing, right? And it rests upon first identifying a particular operator. It goes back, I mean, the notion of Fisher information, I was reading up on all these things, that's an idea which comes out of statistics and probability inference theory. The quantum Fisher information is that, but with quantum mechanical considerations and what you can know and about what you can ask about questions about non-commuting operators. So when we pick a susceptibility, let's say at a finite Q, that essentially means we're picking a particular operator. And so when I do my experiment and I'm looking at, let's say, the electrical response or the data that Sousa, Martin, and Wilkins plotted when they were looking at the response of carbon, diamond, and gallium arsenide, they were asking questions about the electric polarization, so not the magnetization. But as far as the theory goes, in the nature physics of Zoller and collaborators, where they first kind of made this identification, it's agnostic to the particular kind of susceptibility. that's there. So you can write down different forms of the susceptibility, and the fact that one susceptibility is at Q equals 0 and the other one is at finite at finite Q and the other one is at 0Q. This makes no difference to the kind of general. You may not get all the information you need because this, in order to construct, I mean, the way to think about it, if I have a spin system, is that in order to construct, let's say I have extended states and I have some magnetic system which is ordered. In order to construct some extended states that are kind of associated with that, maybe I have quantum Fisher information that tells me I have more than one spin participating in this object at pi because it's an antiferromagnet, and there's some entanglement in the ground state because for reasons that we identify with antiferromagnets. But that entanglement may not be necessary as an important part of the wave functions at Q equals 0, and I just wouldn't see it in my experiment. Yeah. So that's the consideration. Yeah.
Let's take.
Yeah, I have basically from objectivity you can extract the effective mass, and the effective mass can also be extracted from some dynamic fashion, like the specific heat, gamma coefficient. So are they basically the same?
Well, so the question was whether the mass you get from optics is similar to that as the mass from heat capacity, and so that was that plot that I showed you. They either are or not the same depending upon how much you worry about log-log plots and scatter. Let me go back. There, right? So the horizontal of this is the heat capacity, and the vertical of that is the mass extracted from optics. Essentially, the integral of something which looks like the Drury response. And so, yeah, so this is plotted on log, it's 3 orders of magnitude. That's pretty good. But it's log-log, and there's a fair amount of scatter. So, I wouldn't defend the order, numbers of order unity with this plot, but I still think it's, quite remarkable when you think just how different those experiments are. And the caveat I gave was even at the level of Fermi liquid theory, we don't always expect that the same quantities which have the units mass are the same. So, for instance, like quantities like the spin susceptibility typically won't pick up contributions to mass normalizations that come from electron-phonon interactions. But the heat capacity does. The what?
What about the non-Fermi where gamma is divergent? Do you have mass involved?
So it would be interesting. So it's hard. So it's divergent in some non-Fermi liquid, perhaps logarithmically, and so it's hard to see logarithmic divergences. So I think that's one important consideration. There has been no evidence for logarithmic divergences in an optical response for an effective mass. It's something that we're interested in, and I have some hopes that we can either look for it or at least probe for this kind of thing in some of these cyclotron resonance experiments we do at high magnetic fields. Cyclotron resonance is notable in that it picks up contributions to the renormalized mass in a very different way than other quantities. However, there's an idea about Galilean invariance and Cohn's theorem. Materials like heavy fermions or cuprate superconductors are certainly far from being Galilean invariant. But these are kind of important considerations that come in, and in principle can be looked for. Nobody has ever seen that as far as I know.
So, Peter, following up on this quantum Fisher information.
Yeah.
So in a spin case, one knows how to do the normalization.
Say it again, what?
In a spin quantum Fisher information case, one knows how to do normalization, knowing the size of a spin, et cetera, et cetera. In this SWM case, it seems to be a delicate.
I think you're right. Yeah, it's a delicate I mean, it is only affecting things by a constant. So if you have a quantity which is, let's say you imagine tuning something through like the plot I gave of the Chern insulator, and maybe you wanted to look for the logarithmic divergence in this quantity as you go through the Chern to normal insulator transition, you wouldn't care about the overall normalization. There are cases where the low energy complemented bands is kind of far enough removed from everything else that maybe this normalization can be done about the density of charges in a kind of unambiguous fashion, maybe a 2D electron gas that's near a phase transition or something. Our application of this is on phosphorus doped silicon, where you can bring it through a metal insulator transition. And there we know the number of charges because it's equal to the number of, it's one charge per phosphorus. So there are other cases. So if I was interested in doing this on a kind of a complicated multi-band metal, then indeed I'm going to start to have to make a judgment about what's the density that I put in if I really want to get a length scale out. And, I think then it's a matter of, whether or not, that's, that normalization is important for the physics that you want to, physics point you want to make.
We should follow up on this, but the aspect of how do you construct the eigenvalue spread that gets you the certification.
Yeah.
One needs to think about it, I think. It seems,
Yeah. So if you write this in terms of conductivity, it's sigma divided by omega. So the high frequencies matter less. So that's an important consideration in terms of the practical matters. I think what is completely ripe for, let me say one thing, what is completely ripe for theoretical input, though, is that there's a large body of work on partial sum rules of the F sum rules, the integral of the optical conductivity. That's what I showed, right? How does the effective density change as I change that limit of the upper integral? I have maybe some rigorous feeling, and I certainly have intuitive understanding of the kinds of different physics that I get as I increase that integral to higher and higher frequencies. I don't have that for the SWM sum rule. And so that, I think, is a really ripe area for theoretical inquiry, is how do I, how do these partial sum rules work, and what kind of information that I can extract out of them different from the full sum rules? I don't know.
Let's thank Dr. Armitage again.